All right, step 1 says be careful and do not just let go of the spring and let it recoil rapidly. Control the ends and let the spring recoil gradually. Take a super slinky and stretch it out about 3 or 4 meters between 2 students. Do not stretch it too far or you can permanently deform the coils. One student wiggle the slinky continuously up and down and observe the waveform while the other one holds it still. One of you hold it still and one of you just continually. Can you get more waves in it? Okay, well, easy. So your waves are going really high, right?
Yeah.
Which means you have a high, amplitude. Okay, and so try to put in you're putting in energy, but try to put it in where it will show more frequency instead of more amplitude. Yes.
Ooh, nice.
There we go. Okay. All right. So.
Everything reminds me of her.
All right. Stop. It says to draw a sketch of the waveform. So on your papers, you're going to draw a sketch of the waveform. You're simply going to be is that not what it looked like? Yep. It says this is called a continuous wave. The peaks are called crests. So label one of the peaks. Label one crest. And the valleys are called troughs. So go ahead and label a trough. The distance between peaks or trough is called a wavelength. So this could be a wavelength. Put on marker. This could be a wavelength. Or this could be a wavelength. Okay. All right. Brent and Dee, can y'all replicate the wave that you just did? Yeah. Okay. So now what I want you to do is I want you to wiggle the slinky so that your arm moves a greater distance up and down than the waveform you just made.
Just him?
Just him. One of you stay still.
You too? Is that what it is?
Okay, so what's happening to the wave when he's moving a greater distance?
Frequency's going down,
Frequency went down
Yeah.
amplitude going up.
and the amplitude went up.
Yes, sir.
All right, now wiggle the slinky so that your arm moves a shorter distance from side to side or up and down than what you just did. Okay, I think that's about the original. Go even shorter distance. No, shorter. Okay, what happened to the wave? What's happening?
Getting shorter,
It's flattening out, right? So what's happening to your amplitude?
decreasing.
It's decreasing, okay? So the properties of the wave that you're now observing is called the amplitude. The greater the energy used in making the wave, the more the medium is displaced as the wave moves through it. All right, stop. So it wants us to, in number 4, sketch the two waveforms. So if we sketch it with more energy, what is that going to look like?
With more energy?
More energy, what did it look like?
Oh, yeah, so the amplitude was higher.
Taller waves, right?
Yeah, taller.
And less energy look like
Lower waves. Short.
short waves,
Short.
like flatter waves, like that, right?
Yeah.
Okay. So would we be correct if we said amplitude increases as energy increases?
Yes.
Yes. Would we be correct if we said amplitude can decrease as energy decreases?
Yes.
Yes. Okay. Alright, and the next one says have one student wiggle the slinky up and down and have the other student hold the other end of the slinky still. What do you observe about the other student's hand? Can you tell that the wave is transferring energy from one student to the other? What is the evidence? So, what do we see? D is supposed to be holding the slinky still. What do you see about D's hand?
It's moving.
It's still moving. Why is it moving?
Waves transferring.
Energy's
So-
going that way.
He's still receiving energy, right? And energy, you can't just stop it. Right? So,
Stop.
can you tell the wave is transferring energy from one student to the other? Yes. What's my evidence that Brent is transferring energy to D?
I'm moving his hand.
His hand's moving. His hand's moving.
You're-
That's on number 5. You need to be writing it down. That's on number 5.
My hand's moving. Why is his hand moving? You feel that? And then it stops, and then it goes that way. It's twice.
Turns it around.
Like right now.
That messes up my eyes so
Yeah, that
much.
is going over here.
Alright, number 6. Number 6 says wiggle the slinky slowly. Who's going to be still on this one and who's wiggling?
Let's go.
I will
Okay?
slowly.
It says wiggle the slinky slowly. Then wiggle the slinky faster. The number of wiggles per second is called the frequency and is measured in hertz, which is cycles per second. Draw a sketch of the two waves. So let's do it again. Wiggle the slinky slowly. So really you just have half a wave. Alright, go faster.
Dang. My wiggle game is off. Look at those waves.
So we got one big one. Can we make it to where we have lots? Can you get lots in there? Go for more frequency instead of more amplitude. I think you're going for more amplitude. Go for more frequency.
No distance, yeah.
There we go.
Like 3, yeah.
Yeah.
Can you get to 4?
That's the max.
Okay,
That's the
no,
max.
we did.
Alright,
You can
three.
make 4. I've made
I
4.
can make 4? Let me see.
Still 3.
Oh, it's trying.
Nah.
Let me try.
Yeah. Hey, man. You're nice.
There we go.
Very nice.
I think when you're upstairs,
All right, stop. So we want to sketch that wave for number 6. We're going to sketch the wave. So this is number 6. So slow. What did it look like? Just like half a wavelength, right? Because you just have the crest. You don't even have the trough of the wavelength. But when they wiggled faster, we got up to 4. So that increased our what? Frequency. So look, when you add energy to a wave, it can do one of two things. You're either increasing your amplitude, or you're increasing your frequency, or you might be increasing both.
Which one of these has more energy?
You tell me.
I think it's first. It's got more amplitude.
It's got more amplitude, but well, do it. Make the first one. Make the second one. Which one are you exerting more energy for?
This one's definitely harder.
Okay, so that one definitely has more energy. You're having to put out more energy to make that one happen. All right, number 7. Notice the wavelength of the low frequency waves and the high frequency waves. What happens, listen, what happens to the wavelength when the frequency increases?
You get
Wave
shorter.
length decreases.
It gets smaller, it decreases. They're shorter waves, right? What happens when the frequency decreases?
It increases.
The wavelength increases. Wavelength increases. You're doing the next step without me even reading it.
Okay, I want to see. Go.
You're a step ahead.
It's for just the content. It's for content.
Better content.
Alright, so number 8. Wiggle this. Alright, get it still. Get it at equilibrium. Okay. Wiggle the slinky just once and observe the waveform. Draw a sketch of the waveform you observe. Okay, so you did it just once. What do you see?
It, whenever it goes down, it bounces back, comes back.
You see the wave, you see that one little wave traveling, right? You see that one wave going through. That's called a wave pulse. A wave pulse. So draw a sketch of number 8, the wave pulse. I would do it. You have a wave pulse. I would probably do just kind of like this. You see one wave traveling through.
I'll shoot an arrow.
You might do it again. Do the wave pulse.
To the wave. Some of the wave.
Oh, man.
So you might, you got a little bit of
That wave one time.
like that. I forgot the trough there.
Started a new group called the Wave Boys.
Copy, baby.
Manager. You're the owner. What do you mean, brother? Yeah, you're the owner.
All right.
Listen, bro.
The types of waves you have been observing are called transverse waves because as they travel down the slinky, they vibrate up and down perpendicular to the direction of travel. So which way is the wave traveling? Yes, between left and right, between Brent and D, right? And then which way though is the medium traveling? Up and down. So you've got the medium traveling up and down, you've got the wave going that way, so they're perpendicular. So that's why they're transverse wave. Alright, what's that, number 8? Number 9. Now, quickly push the end of the slinky towards the other student. Just push it.
Like this.
Just like that.
Feel that?
This is a different type of wave. Notice that the wave pulse is composed of coils compressing together and then stretching further apart. This kind of wave is called a compressional or a longitudinal wave. So what y'all might want to do is pull, like, have a little slack so it'll pull tighter. You get a little slack too over there.
Oh, okay.
Mess up the cool.
Oh, okay.
Okay?
Hangs when
No.
do a rotate.
Because when it's still doing this when y'all were doing it earlier, so just so now you can see the coils compressing a little bit better because it's you see the wave. I mean, obviously it's making a transverse wave, but can y'all see the longitudinal wave? Okay, so when it's compressing. When it's compressing, it's spread out, right? And then as the wave gets to it, it gets closer and spreads out, right? So which way is the medium moving? Left and right, side to side. Which way is the wave moving? Side to side. So they're parallel to each other. So that's a longitudinal or a compressional wave. All right. Says now push the coil repeatedly at a slow rate. One of you holding it still, one of you pushing. And then at a faster rate. Notice the wave patterns and coils of the slinky A wavelength in this type of wave is measured from one set of compressed coils called a compression to the next compression. The stretched part of the spring is called a rarefaction. Alright, so when you have it where it is stretched out, that's that's a rarefaction. Stretched out. Compression is when it's together. Rarefaction, compression. Okay? What?
Did that 10?
Yes, that was 10. Alright, so number 11. Notice the wavelength of the low frequency waves and the high frequency waves. What happens to the wavelength when frequency increases? They get shorter. So try to do a quicker compression. Now do slow. It's harder to see in this one, but the wavelength does gets shorter with the low frequency. I'm sorry. The wavelength gets shorter when the frequency increases. It gets longer when the frequency decreases, just like the others. All right. We now want to determine what factors determine the speed of a wave. We will be making only transverse waves, so the up and down, not the compression, the up and down again.
Oh, nice.
Also, we want to keep the Slinky stretched the same distance for each trial. It may be hard to tell the speed of the wave without using a stopwatch to time a wave traveling from one end of the Slinky to the other. We're going to make a data table to keep up with the name of the property of waves you are testing, the type of change you are trying, and the time it takes a crest to go from one end of the Slinky to the other. Keeping the total Slinky length the same, keeping the total Slinky length the same the Slinky at different, that's a tongue twister, at several different frequencies. Measure the time it takes a wave crest to move from one end of the Slinky to the other. Enter your results in a data table along with the total length of the spring. Calculate the wave speeds, and what do you notice about the wave speeds? So we're going to stop here so we can measure a length. All right, so we're going to film, and we're going to start on number 12 on the wave behavior. We're going to keep the Slinky the same length, and we measured it out. It's 3.35 meters. We want to get the time that it takes to go from our left side to the right side. Okay, we're going to go left side to the right side. So give us a low frequency wave, and let's get the time. 0.50 seconds. Okay. All right. Write that down, and we'll write them all down again at the end. All right. Let's do a medium frequency wave. .43. Medium frequency was 0.43 seconds for the period. Now try a high frequency wave. .32. All right, so take a break. 0.50. And this is in seconds.
What's the last one?
0.50, 0.43, 0.32. Now granted, Devin's reflexes are really quick, but this is hard to do, okay? So, probably not exact. But how do we we calculate the velocity now? Velocity is equal to distance over time. So somebody's got a calculator. Let's do this real quick. Distance over time.
The first one is 6.72.
6.72. That's going to be in meters per second.
The second one is 7.81.
7.81. What's the third one?
10.5.
10.5. So a little bit of a jump there. All right. So really, what we
I think we lost it.
What we should see is that they're kind of similar, and the first two are really similar. The third one, the speed jumps up a bit, but we should see, what do you notice about the wave speeds? Honestly, we should notice that the wave speeds are similar. We need to notice that the wave speeds are similar, number 12. It says the frequency of the wave is how many complete wave cycles happen per second. The frequency is measured in hertz, which is cycles per second. The period of a wave is the reciprocal of the frequency and is measured in seconds. So that is that formula, T is equal to 1 over F. So for frequency, we have T is equal to 1 over F, so that's how you'll find your frequency. So I want you to, not at the moment, but later I want you to find your frequency, because the bell's going to catch us soon, so I want to go on and do the other two. Since we now want to test the effect of amplitude on the speed of the wave, make a wave pulse, meaning a single wave, and measure the time it takes to travel down the Slinky. Repeat with different amplitudes, keeping the frequency and the total length of the spring the same. Enter your results in the data table, which we've already used up the data table. Calculate the wave speeds. What do you notice about the wave speeds? So we know our wave length is going to be 3.36. I'm just gonna erase. We'll save this, or we'll pull it back up tomorrow so y'all can see another graph, because I know you only have one graph on your paper right now. Alright, so what you want to do, you want to do a wave pulse, and you want to send it from U to D. You're timing how long it takes the pulse to get from Brent to D. And being one wave, maybe it'll be easier to time. But that first pulse, we want to test the effect of amplitude on speed. So you're going to make a short wave, a little bit longer, and a tall wave. Okay, but you're going to do it in a pulse. Okay?
You like that one?
That means you gotta tighten it up.
Yeah, you might want to tighten it up a little bit. All right, so let's do the. Make sure it's a transverse wave, like a up and down. Okay, so you don't want to keep going. You just want to do one wave pulse. Okay. Yes, just like that.
Oh.
About a point 30.
It's 37.
Yeah, that's about. I should think about.
What'd you get? 0.34 for the first one. All right.
I was closer than you two.
0.34. So what is the what's the next one? Do another one with a bigger amplitude.
That's about point 48.
43.
Point 46.
31. It's going down.
0.31. Okay. All right. Now do a really big one.
116.
About a point 12. No, about point
Oh,
21.
Brent, but shot and then
Point
He's getting a lot of the reflecting.
Point 21.
at 31 again.
.34, .31, and .31. So when we,
Serious? That's,
so the distances are the same.
I refuse.
So we got .34, .31, and .31. So what is the speed gonna be here? Same distance, what is the speed gonna be here? Somebody calculate that for me, distance divided by time.
$9.88.
9.88 meters per second, and so somebody do 2 and 3 for me. Divide that by .31.
It's gonna be 10.84, and then it's the same for point.
Yeah, it's the same. So these are number 13, what do you notice about the wave speeds? The wave speeds are very similar in number 13. It says the material the wave moves through is called the wave medium. Its properties determine the speed of a wave traveling through it. We are going to change the medium, which is in this case the slinky, by changing the tension in the slinky. To increase the tension of the slinky, be sure to keep the total length of the slinky constant. Have the student at the other end gather a number of pulls of the slinky and hold them together while the student on the unchanged end makes the wave pulses. That was for the last one, which you did that. You did that. All right. So with amplitude and keeping the same tension, it seemed to be the same. But now we want to test the effect of tension on the speed of the wave. So we're doing the same process. Same process of the amplitude, Brent. So you're going to make a small wave. I'm sorry. Actually, you're going to try to make the same type of wave every time. Okay? You just want more tension. So you're going to try it really loose, and then you're going to get kind of medium tension, and then you want to get it real tight.
Or you can just have B, change his grip on his side.
Yeah.
Change the tension.
Do a pulse?
Huh?
Pulse?
Just one. Just a wave, pulse. A wave pulse.
43.
438.
Go on
That was 437.
35.
.35. Well, let me. I'll erase that when it's done, and we'll rewrite it. All right. So we have .35. Let's try another one. It's more tense this time.
Tighten it up.
34.
.34. Now make it really tense. Just don't let go.
29.
That's not 434.
34.
.34. Oh, well, that would stay the same, and that was one that was supposed to increase. The wave speed was supposed to increase.
Go one time.
Let's try it again.
Can we tighten it up a lot?
You can. D, you might want to wrap it around your hand once just
Yeah, I
to.
can't do this one.
It looked like it had the same tension right before they went.
425.
Ready?
31.
.31. A little bit faster. All right, it's supposed to increase with tension. So that's number 14. The wave speed is supposed to increase with tension.
You go.
Do it one more time.
Hear the sound wave shower?
Yeah, one more.
One more?
431.
25.
.25. It increased that time. So. All right.